everybody. This is your standard disclaimer that you are being recorded and staying in the meeting indicates that you consent. Alright, welcome everybody to our meeting this week on forces and motion in physics. So this is a more basic introductory topic, and let's see where we go with this. To begin, congratulations to all the coaches. We all made a team at Interlake. So when you meet a coach, congratulate them for getting on an Interlake team. Yay!
Don't have to do that.
Yes, you should do that anyways. Don't listen to Abadan. Alright, so to start, today we're going to talk about kinematics, forces and Newton's laws, as well as the angular equivalents of these. So let's get started with first kinematics. Alright, so the very basics of kinematics involves distance and displacement. So the main difference here is that distance is a scalar and displacement is a vector, as well as them being essentially distance essentially being related to a path, while displacement is essentially path independent. What I mean by this is distance is essentially the total amount you travel. If you follow this blue line from A to B, you can notice that this line is longer than the actual displacement between A and B. And this displacement is essentially the shortest distance you can take from A to B. Notably, however, this displacement, no matter how you travel from A to B, you're still going to have the same displacement because A and B are still the same. However, this is not true for distance, because distance, if you go this way, obviously it's going to be longer than going straight. And maybe there's another path where you go all the way, maybe around the other side of the Earth and come back, which is definitely a lot longer than this path right here. So distance is path dependent, while displacement is not. As well as distance is a scalar, while displacement is a vector. Now some of you may already know this, some of you may not, but you can think of a vector as being a value that has both a magnitude and a direction. In this case, the direction is the direction from A to B, and the magnitude is the distance, the shortest distance between A and B. So this is a critical idea. However, in physics, we usually don't really care too much about distance. We don't calculate, we don't do much with it. We're normally concerned largely with displacement. So our next main concept is velocity and speed. So very much like how we had a difference between distance and displacement, speed is a scalar, meaning it's only a value, it's a number, while velocity is also a vector. So you can think of speed as being the magnitude of velocity. So when you're driving in a car, suppose like when you're one of these cars here, and you're traveling at 25 meters per second to the right. So your velocity vector has two components. Well, I can't call them components because that means something else, but it has two parts to it. One, its magnitude is 25 meters per second, and that's also the speed. And second, the direction is that you're moving to the right, at least in our screen right now. So if you're currently the driver inside the car and you look at your speedometer inside the car, it's going to say you're driving at 25 not miles per hour, sorry. It's going to say something in miles per hour, but assuming if we have a meters per second speedometer, it would say you're traveling at 25 meters per second. However, in contrast, if you're in this car, defining the positive direction as to the right, of course, because we usually use that, for example, on a number line, your velocity in this case is instead negative 25 meters per second, because you're moving to the left instead of to the right. However, assuming that your speed is still the same, if you look at your speedometer, you're still going to say 25 meters per second. So that's the difference here. Notice that in these two cases, the speed is the same, but the velocity is different. This basically shows that velocity is dependent on direction as well. Now, how do we define velocity in relationship to speed? To displacement. Well, we know that velocity is essentially how fast you're moving, right? This is you can think of it similar to speed in this case, at least. Now, the very basic way of saying it is the rate of change in position. So if I move 1 meter in 1 second, then my average rate of change of position is my velocity, which is 1 meter per second in this case. Typically, we like to talk about instantaneous velocity, which means my current velocity at this time. So when you're looking at the speedometer in a car, this velocity is your instantaneous velocity because that's how fast you are going right now. Another concept that we talk about a lot is average velocity, which essentially talks about how fast you move over a period of time, and we'll explore that a little bit later. Alright, so as I just mentioned, when we have constant velocity, that's essentially our rate of change. So if I travel 5 meters per second, or at a speed of velocity of 5 meters per second, for 5 seconds, because I travel 5 meters every second, and there's 5 of those seconds, I travel a total of 25 meters per second. And now we can use this principle here with the equation delta x equals vt, where delta indicates change, and x is the variable for position. So we can read this as the change in position is equal to the velocity times the time. Now in this case we're using constant velocity, so it's working out pretty easily. However, sometimes you don't always have constant velocity. You can have changing velocity, but if you have constant acceleration, which we'll explore also in 2 slides, if we have constant change in velocity, you can essentially see the velocity as a linear line, right? And taking the average of it, you can find the change in position. Now you can read this as the change in position is equal to average velocity times time. And this does make sense because we know that average velocity is essentially just defined by total distance over total time. So multiplying by time, it makes sense that we get total distance. So if you do know some basic calculus, or I expect probably large majority of you guys don't, you can also define the velocity as the time derivative of position. This will be explored if you take high school physics. Not too important here. Now let's take a look at this graph. So suppose that we have a velocity y-axis, meaning this 0, 0 point here indicates that at time 0 the velocity is 0, and over here you have 4, 6. At times 4 you're traveling at 6 meters per second. So can anybody tell me how much distance is traveled from time 0 to 2? Do you guys have any idea how much displacement is changed?
2 meters.
2 meters, right? And how did you get that? Well, notice that your final velocity is 2, and your starting velocity is 0. And because your acceleration is constant, you can actually just take the average of 0 and 2 to get 1. So your average velocity from time equals 0 to time equals 2 is 1 meter per second, and you have a total of 2 seconds. So using this second equation here, delta x equals average velocity times time, because average velocity is 1 and times 2, your change in position is equal to 2 at this part. Now you can use other geometric techniques. For example, over here, this from time 2 equals time 4, you can use the area formula of a trapezoid. In this case, you have 2 plus 6 over 2 equals 4. This means that the average velocity here is 4 meters per second, and you have a total time of 2 seconds here. So your total distance traveled is 8. And notice what we're doing here. We're calculating the position change based on the area under the curve here, the area under the curve. And this is a really critical idea. When you get to high school physics, you'll understand this is represented as an integral, but this is a little bit too advanced. Basically here, you just need to remember that you can calculate the change in position by finding the area under the curve of the velocity graph. Alright, so next let's talk about acceleration. Acceleration is a very important, it's a really important concept, and it's related to force. We'll see in section 2 today. Once again, using the derivative, it's the time derivative of velocity. But what you guys need to remember is that it is the rate of change of velocity. You can use the analogy acceleration is to velocity as velocity is to time. Remember that velocity is to position. Sorry. Remember, velocity is rate of change of position, while acceleration is rate of change of velocity. So normally in our more realistic world, when you're moving around, you don't say, oh, I want my velocity to be x, or like 10 meters per second. You can't just directly say that. And suppose you're driving, or your parent is driving. If they want to speed up to get to, say, a different velocity at maybe 20 meters per second, from 10 meters per second, they can't just say, I immediately want to go to 20 meters per second. They have to apply an acceleration to get to that part. And this is deeply related to how much force is applied, as well as a mass, as we'll see in Newton's second law today. So these are the main four kinematics equations. So this entire time we were talking about kinematics, which is defined as the study of motion. So these equations are all the very important ones. Today we'll talk about 1, 2, 3. Number 4 is essentially obtained by manipulating the variables and substituting around. But let's talk about the first one. So we know that, okay, so we'll define this as the v is the final velocity, v naught or v sub 0 is initial velocity or starting velocity, a is acceleration, and t is time. So suppose we subtract v0 from both sides, so we get v minus v0 equals a times t. V minus v0 then is essentially the difference between the ending and the starting velocity, or in other words, delta v, or the change in velocity. Now, our equation then tells us the change of velocity is equal to acceleration times time, and that makes sense because acceleration is the rate of change of velocity per unit time, is the change in velocity per unit time, right? So by multiplying by time, we essentially get the change in velocity. So this first one makes sense. So here's one to remember: v equals v naught plus at. The second one is the change in position is equal to the average velocity times time. So we actually talked about this about 2 or 3 slides ago, where v is the final and v naught is the initial. And we're taking the average of these two because we're assuming acceleration is constant, which we're assuming in all of these equations actually. So now, because we know that the v plus v naught over 2 is equal to the average velocity, we can obtain the change in position pretty easily just by multiplying by time. All right, so our third equation is slightly more complicated. It tells us that the change in position x is equal to the starting velocity times time plus 1 over 2 at squared. So this one is a little bit harder to explain. So let's use a graph for this. So notice that we have this, suppose we have this time, this graph, and this is velocity on the y-axis and time on the x-axis, very similar to this graph here. Now notice here we calculate the change in position by calculating the area under the curve. Now we can do the same thing for here, right? So the idea is, suppose we start at a time 1 and a time 2, right? And we want to find the change in position in this time. Well, our first velocity point is here, and our second velocity point is here. So here, instead of using just v itself, they've used v sub f, which indicates final, which is the same thing as just v. So we want to find the area of the curve from right here to right here. And the easiest way to do that, you could use the average velocity formula, which is v0 plus vf over 2 times t. That would be the easiest way, but sometimes you don't know what vf is, and they don't give it to you. They only give you the acceleration. So notably, acceleration, remember, is the rate of change of velocity, or in other words, the slope. In this case, because velocity is increasing at a constant rate, the slope of this is constant as well. So a is equal to some constant c. Now let's see what happens when we try to what happens when we try to calculate the area under the curve. So without using our trapezoid method, assuming we don't know this this value here, we can split this into two parts, as you see here. We can split it into this rectangle. This looks like a square, but it's only a rectangle right now. So we can split it into this rectangle as well as this triangle here. So first of all, this rectangle, the height here is v naught, or the starting velocity, v0. And we can just assume t2 minus t1 is t. So the base is just t, or delta t in this case. So the area of this is v naught times t, which is reflected right here. So this is our v naught times t term. However, we now need to calculate the area of this triangle here. And we know that the base is t, because it's the same as the base here. Now what is this value? Can anybody tell me what this value should be?
Instant velocity?
Not quite. Notice that our slope is given by a, right? Acceleration a. Now, the slope is defined as the rise over the run. Some of you may have heard of this. So the rise in this case is a change in velocity, and the run over here is the change in time. So when we multiply acceleration by time, we actually get this height here. So this is equal to at, and this one is equal to t. So by our standard base times height over 2 triangular formula, we get that the area of this is 1/2 at squared. And that is exactly this term right here. So that's where we get this formula from. If you wanted to, instead, you could try substituting the first two equations to also obtain this. But I find this approach much more intuitive and easier to understand. So remember that, most importantly, position is equal to the area under the curve of the velocity graph. Give me a second, I'll drink some water. Alright, let's continue. Next, we're talking about forces. So the main definition of a force is a push or pull on an object. So maybe if I give you a push, then I'm giving you a force. Other forces include gravitation. For example, you feel attracted to the ground. That's a thing. The normal force, which we'll talk about later, friction as well. So there's a concept that I have to introduce to you here called the net force. And then what the net force essentially details is the total sum of all forces on an object. So for example, a very basic example, if I have a wooden block and I'm pushing it from one side, but I'm pushing it equally as hard from the other side, although I am exerting force on it, the net force is 0 because it essentially balances out. However, in contrast, you can have other forces that make it unbalanced and thus cause acceleration, which we'll talk about in 2 slides exactly. Oh, 3 slides, sorry. So our first, we have to talk about Newton's laws, because Newton was, extremely brilliant, and he developed this set of laws. And what essentially they describe is how forces interact. And there are 3 basic ones. Let's start with the first one, which is the definition of inertia. So inertia, in this definition from the NASA website, is that every object persists in its state of rest or uniform motion in a straight line unless it is compelled to change by that state by forces impressed onto it. So this is a rather long explanation. The simpler way to say it is just a matter at rest tends to be a mass at rest tends to stay at rest. Meaning, if I'm staying here and I'm not moving, without any forces, I will stay at rest. Whereas if I'm in motion, I will keep that motion unless somebody makes me stop. Pretty simple, right? But you guys might be wondering, some of you who may be less familiar with physics might be like, oh, if I take a block and push it on the ground, and I let go of it, I'm not putting any force on it, so why does it stop? So this is in part due to friction, which we'll talk about in a couple more slides. So the next slide is on Newton's second law, which is extremely famous and also extremely useful. So it essentially states that the net force is equal to mass times acceleration. So I've put 2 here because it depends on whether your acceleration is your overall acceleration or acceleration due to one part. So usually we are more concerned with this F net equals ma. Essentially this net just means net force. So it means that overall, if I have 1 Newton of force, don't forget Newton was so famous that he was the unit was named after him. If you have 1 Newton of force, net force, then I will be accelerating to one direction, and that direction must be the same direction as the net force. If you remember our discussion of vectors earlier, force is also a vector that is well used. So this is just something to remember. F equals ma, extremely important. Write this down in your notebook. Put it on your hand. Don't forget this. So this equation essentially relates the force that we apply to our object to the mass of the object plus acceleration. And this is essentially intuitively obvious. Suppose I push something really heavy. I'm only expecting it to move a little bit because it's really heavy, right? However, if I'm instead like throwing a tennis ball or a baseball, because that's a lot lighter than maybe my refrigerator, you can expect it to accelerate a lot more. Newton's third law essentially describes force pairs. Now notice how I have bolded words here. These bolded words are essentially what the main points you probably want to remember, except for this one, of course. This one you just remember F equals ma, you're good to go. So this one essentially describes the law of force pairs, where for every action there is an equal and opposite reaction. So if this man steps off the boat, his action is stepping off the boat, whereas the boat moves backwards as essentially a reaction. In this case, of course, we're talking about forces as actions. So let's do a little bit of practice. So can anybody tell me what the opposite force or the force pair is when you slap a wall? Say I slap my wall. What's the force pair?
It can also be, depending on how hard you slap it, that the wall crumbles.
Yeah, we're assuming
Well,
in physics we usually assume ideal situations where your wall will not crumble.
okay, well, if the wall is sturdy enough, your hand will bounce off the wall. If your hand doesn't break.
That is very close. Essentially, the opposite force here is the wall hitting your hand. So when you slap the wall, you exerted a force on the wall, but then the wall also exerted a force on you. Now, here's a more classic example. Suppose you're sitting on ice, and we're assuming ice is very slippery, and you throw a ball away and you go backwards. What is the opposite force in this case?
Moving backwards.
We're looking for the specific force. And notice how earlier I talked about you hitting the wall and the wall hitting you. In this case, you're throwing the ball, and the ball is kind of throwing you away. And that's why you're moving backwards when you throw the ball away. And this also has to do with conservation of momentum, which is out of the scope of today. Now here's a question for the more advanced physics people. Suppose you're standing straight up on the earth, and the ground pushes up at you. That's how you're standing up, right? Otherwise, you would just fall down. What is the opposite force of the gravitational pull of the Earth? Does anybody have any ideas?
You are hitting the gravitational pull.
You're not. The gravitational pull is not really hitting you, but essentially Earth is pulling you towards it, right? The opposite is you pulling the Earth toward you. The opposite is you pulling the Earth towards yourself. Now this seems kind of counterintuitive because it seems like the Earth is so much bigger than you, right? And you shouldn't be able to pull it towards you. But that's actually not quite true. It's important to note that the force exerted by the Earth on you is the same as the force you exert on the Earth. The notable part, however, is that the Earth has a lot more mass than you. So when you go to this equation, your mass is really small, so your acceleration is easily noticeable. However, because Earth's mass is so big, the Earth's acceleration relative to you will be very small. And finally, what is the opposite force for a normal force? This question you'll see on your extension for today. First here, we'll talk about normal force. So the normal force is a type of contact force, meaning you have to be in contact for it to occur. This is not true for gravitational force, electromagnetic force, etc., etc. This essentially prevents objects from moving through each other. So when I'm standing on my floor, the gravitational force is pulling me down, but the normal force essentially rebalances it to make sure I don't go flying straight through my floor. Now, the normal force is a really interesting force because it's not fixed. The gravitational when I'm standing in one place, like the same distance from Earth, my gravitational force is the same, assuming my mass is fixed, of course. However, the normal force depends on the angle that I'm standing at, if I'm standing on a slope, as well as a number of different other factors. So this is a quite interesting topic. The main thing to know here is that it's enough to counterbalance gravity. If you're not standing on a slope, normal force is just equal to the gravitational pull. The next thing to note is frictional force. So friction is known as a non-conservative force because it does not conserve energy, and we'll talk about that in about 2 slides. Friction always resists the intended direction of the motion, and the reason behind this is because if you look at the very, very small, almost molecular level, materials are always composed of bumps, no matter how soft something looks, be it silk or ice or polished mirrors, they always still have these tiny bumps. Well, this can also cause a lot of problems for astrophysicists. But in our case, when you're walking around, well, first of all, say I'm walking around on the ground. If I don't have frictional force, I have no ability to move forwards because I essentially can't put any force on the ground. So friction is actually really helpful, and there's essentially two different types, static and kinetic friction. But this is a topic for a different day. All you need to know is that it's a non-conservative force, and there's a formula for it, which will be included in your extension, which I totally recommend you guys to do. So let's finish up because we're running somewhat out of time. So let's go a little bit faster. We have our four fundamental forces: gravitation, the weak nuclear force, strong electromagnetic, and strong nuclear force. These are in order of strongest to weakest, with the relative strength here. So if the strongest weak nuclear force is given a value of 1, electromagnetic would be 0.001, weak nuclear would be 0.000 with 15 zeros, 1, and gravitation would be even smaller. Notice that we have 4 particles here, well, 5 including the W and Z bosons. The graviton, these particles are all the carriers of this force. Notably, the graviton is theoretical. Nobody has actually observed this, but some physicists believe it to exist, and it would make a lot of things nicer if it did. W and Z bosons are the carrier of the weak nuclear force. This is something just to write down and remember. Photons, some of you may know, behave as particles and waves, which is really interesting. And they carry electromagnetic force. And the strong nuclear force is carried by gluons. And the way to remember this gluon is it's essentially like glue. It glues the molecule together. And that's why it's got a glue. The nucleus. So non-conservative forces. Conservative forces are forces that maintain that the total work done is independent of path. So for example, gravity. If I'm trying to go from one location to the other location, no matter if I go straight up or all the way to the side and then to that place, the total force I use to overcome gravity is the same. However, friction is not the same. For example, if I want to move 1 meter to my right, but I first move 1 meter to the left and then 2 meters to my right, I travel more distance, and this causes more energy to be wasted, essentially. That's why friction is a non-conservative force. It's only conservative when the path does not matter, similarly to how we talked about displacement earlier. So finally, we have 3 slides on angular motion. Angular motion, so normally we've been talking about moving in straight lines or on planes. Angular motion is what happens when you move around in circles, which is very, very similar, actually, more similar than you might think. So similar to how we have normal displacement, normal velocity, and normal acceleration, we also have angular displacement, angular velocity, and angular acceleration. So displacement is normally in the international standards denoted by s, but in the US we use delta x. Here we use theta, the Greek letter theta, to represent angular displacement. And notice that we've related s and theta here to each other through the radius r of travel. Velocity, instead of using v, we use the Greek letter, which is very similar to a w, called omega. And finally, for acceleration, we use alpha, which looks a lot like an a. So you can kind of get where they got these ideas from. And time isn't different in angular systems, so time is still just t. Now, the interesting to note here is we can essentially copy all of our equations from earlier. So if you notice, these are the exact same equations from earlier, except, of course, these two are actually flipped. It doesn't really matter which order they rotate in. We can substitute angular displacement in for displacement, velocity in for angular velocity in for velocity, and angular acceleration in for acceleration, and all of these still hold. You can derive these by yourself and find that they work. So you can just essentially substitute them. Now, the final thought that I'll leave you guys with is that you can also apply Newton's second law to angular motion, except similar to how we had equivalents for displacement, velocity, and acceleration, we have the equivalents here as well. Instead of force, we have something called torque. So this is represented by tau, and net external, essentially the net torque. on a system. I is the equivalent of mass. In this case, it's called moment of inertia, which is a really long name. I don't know why they call it that. Most people actually want to change it, but it was created a long time ago, so that's what it is now. So I is essentially the moment of inertia, equivalent to mass. And alpha, we talked about this earlier, it's just angular acceleration. So if we put them all together, we essentially get Newton's second law, except in angular terms. Alright, now let's end the recording here.